Want to read just a quick paragraph from the text. We'll discuss many of these structures, including the hippocampus and amygdala, in the chapters to come. For now, we're going to focus on the cerebrum, the largest structure in the brain, and that includes the cerebral cortex, consisting of about a half dozen layers of neurons with white matter beneath, which carries information between the cortex and the thalamus, or between different parts of the cortex. And this is where the action is. This is the important part with respect to neuroscience. And she has a decent illustration here, although there are 1,000 of them on the internet, of course, millions, literally. I want to bring into attention a few of the lobes that are on the bottom left there. The occipital lobe is responsible for vision primarily, and that's kind of ironic because the eyes are on the opposite side. So there's neural fibers that have to carry information from the eyes to your occipital lobe, and it travels a rather large distance. But nonetheless, that's the organization. The temporal lobes, and you're looking at the left hemisphere there, the left side of the brain, responsible for hearing, but a good number of other things too. And you could tell by their placement that that's sort of ideal. The parietal lobe, and I'm oversimplifying here on purpose, but has the capacity for sensing and for really, really fine sensing. So as I'm rubbing the palm of my hand on my leather desk cover, I have one of those, I forgot what you call those things, blotters. That information is going from my right hand to my left parietal cortex. It's contralaterally organized. And there's a place at the very front of the parietal lobe called the somatosensory cortex that's unevenly distributed towards the major parts of your body that are responsible for sensing, like your hands and fingers, like your tongue and lips, and your cheeks, and also reproductive organs. And why might that be the case? Those are the places where tactile or touching sensitivity is the most important. On the other hand, there's relatively little space doled out for elbows and kneecaps and shoulder blades. You can feel things there. I would feel a bee sting, but it's not nearly as important for me to have sensitivity in those other places than it is in my tongue, where I can instantly tell whether milk is sour, or I can instantly tell if a bee is near my cheek, or I can instantly tell if something's hot on my hand. So I've got a disproportionate allocation in that parietal lobe in the somatosensory cortex near the front of it. Now, the last lobe, the frontal lobe, which we'll speak of with respect to personal governance, with respect to restraint, thinking, planning, everything that makes us human, everything that makes us adults, certainly, is contained in that frontal lobe. Near the rear of the frontal lobe, to the back of the green part, is the primary motor cortex, which is responsible for our fine movements. You have gross movements in your thighs and your biceps, forearms, torso, when you're walking, etc., movements. Those are large muscle movements. They're gross, and that's what gross means in that context. Whereas the movements that you have with your fingers, tying shoes, playing musical instruments, typing, putting on a necktie, fastening buttons on clothing, what have you, those are fine movements. They have to be pretty exact. And they're governed by the rear of that frontal lobe and the primary motor cortex. And so it goes with your tongue. You think of the way that your tongue coordinates with the rest of your mouth to produce consonants. For instance, I can say cherry sherbet, CH hard, SH soft. I can say the thick thorn, soft TH, harder THs on the thick and the thorn, etc. Korean, the language in Korea has, I think, 6 different Ks, hard K sounds that we could barely discern as Americans. But that relies on the sophistication of the tongue. Imagine what it takes to chew, how sophisticated that is. You don't just chew by moving your molars up and down. They have to move up and down in concert with your tongue, and there has to be a judgment at some point on when you're ready to swallow. And that is a really, really fine skill. that keeps us alive. That's a very, very fine movement there that's governed by the rear of your frontal lobe, of course. And you think how fine it is to blow a bubble chewing gum. It's incredible. When you think how difficult chewing is, you're constantly sending the food back from the middle of your mouth over to your molars to do that. So that's that primary motor cortex there. That's in addition to thinking and planning and personal restraint is a very important part of the frontal lobe. And you can see it's divided here color-wise. Purple for basically the primary motor cortex, and here's sort of a blue color for the somatosensory cortex. Pretty cool. It's amazing how sophisticated we are. And if you ever want to, you can go Google a homunculus, basically how our bodies would look if our physical person looked like the way that they're apportioned in the brain. But with respect to that motor cortex, of course, our fingers and our mouth get all the action, where the rest of our bodies, it's not important that your thighs move exactly the same way every time. That's gross, and it's not critical to life functioning. So kind of a cool idea. On the left part of the forebrain, Broca's area, which is responsible for the production of speech. So if I ask you a question, how old are you? And someone says 19, that's Broca's area. They know the answer, and you have to produce fluid speech to be able to sort of spit it back out. And stroke victims often lose ability in Broca's area, and they don't produce language very well. It's a halting speech. And then a little bit to the rear of that is Wernicke's area. In this case, it's the reverse, where a person has very, very fluid speech, but it's nonsensical. They're saying things that just don't make a lot of sense. And this is equally an issue often happening with stroke victims. Now, these areas tend to be on the left side, the left hemisphere, because that's where language lays. But I will say it's interesting that female stroke victims tend to do better. And one reason is because males are lateralized more heavily to the left hemisphere than females. So not all parts of biology that pertain to gender or sex are, I want to put this the right way, many things are genuinely divided by sex, not just sex organs, but there are a good number of traits like that, like stroke recovery rates, that can be rather well predicted by birth biological sex. So make of that what you will. It's just an interesting part of gerontology and that sort of field of stroke recovery. Okay, well, I'll come back in a minute. We'll speak of a little bit more about the forebrain and the frontal cortex, frontal lobe.